and get started. Alrighty, let's kick this back. All right, actually real quick, just in case. Anyone who just came in, if you could be so kind as to quickly scan that. Shouldn't need to log into Gmail or anything, you should just be able to fill it out. Just quick, just getting some details about everyone showing up. That's good for metrics. And then at the end, there'll be a sign out, which just lets you ask for different topics. We have access to a lot of speakers across the street at all the various companies. So if you have a specific topic you're really, really interested in, and you recommend it to me, I can probably find someone who can come speak about it. So let's get started. So to begin, you're all probably familiar with the title of what this talk will be. So this is Introduction to Electromagnetic Pulse and High Power Microwave Technology. So this is a really high level thing. A lot of this stuff is classified. So we don't just have it available to us. But the broad concepts and information necessary for if you, for example, wanted to make a small version, we can get you up to speed, at least with the design understanding of what you would need to make an effective EMP, an effective microwave device. So this is presented by me, Ethan Hoban. Who am I? I'm a graduate of the UAH Electrical Engineering program here undergrad, and I'm working on my thesis now. Soon I will no longer have to do school. Yay. We'll see. I'm employed at Northrop Grumman. You can see me in my famous picture there. I'm a full-time Tempest engineer, and recently given additional tasking as a stealth engineer and electronic warfare engineer at Northrop Grumman. 60-hour weeks, yeah. Habitual project collector. I'll give you all this tip now if you haven't gotten this yet. If you just go to class and get 4.0, that is not enough anymore. You got to be doing this stuff in your bedroom, and that'll give you a really big leg up. The recruiters like to see it, and hands-on experience is always better than theoretical experience. And then rocket enthusiast, by the way, I flipped that switch 20 seconds before it exploded. That did not go properly. All right. So, what to expect at a high level. We're going to do a quick introduction to EMPs. I'm sure a lot of you guys may have a conception of what they are from science fiction, that kind of stuff. Maybe you threw an EMP grenade in a video game at some point. I can assure you they work a little differently, but not that much differently. We'll go over concepts for EMP generation. What are the methods in nature that can generate these things, and how do we generate them artificially when we want to? The effects of EMPs, how to optimize the effects of EMPs, because that is the trick. And then we're going to talk about the second half, which is high power microwave technology. This is technically a subset of electromagnetic pulses, but it's the new thing. This is what everyone's doing. This is the stuff that the US military is investing billions in as we speak. And we'll talk a little bit about that a little farther on. And then towards the end, we'll take some questions, and then we'll cut the recording, and I'll let you guys in on some cool new stuff coming. So, let's continue. Yeah, real quick disclaimer. I've worked on a lot of stuff, but I haven't had the pleasure of touching EMPs yet. I promise this is all public release information. I am not leaking anything today. And that's a War Thunder meme. All right. So, broad beginning. Electromagnetic pulses. Basically, at a high level, all it is doesn't even necessarily need to be a high amplitude, but at a minimum, it has to be an extremely fast change of the electromagnetic field. They're also known as transients, and basically, what you guys are familiar with, though, is ultra-high energy EMPs. The most common historical version of these is coronal mass ejections, solar flares. These are the types of things where large amounts of magnetic particles interact with our upper ionosphere and create massive fluctuations in Earth's magnetic field, which result in geomagnetic storms. So a lot of historical effects. There was an 1800s, telegraph wires, all of them exploded across the country. That wasn't great. And then if that were to happen today, yeah, it wouldn't be great for whoever's facing the sun at that moment. And also, lightning strikes. It's a localized EMP, but in terms of absolute strength near it, it's relative to a coronal mass ejection or a solar flare. This right here is a demonstration and an analysis about an artificial EMP. I kind of already gave it away there, but the most popular method for an artificial EMP is a nuke. Nuclear weapons, funny enough, if you think the explosion of the nuclear weapon is the scariest part about it, not really. From a military perspective and from a civilian safety perspective, the EMP is far more dangerous and far more widespread. The nuclear explosion may only affect that little dot, but the EMP effect, 720,000 square miles, all electronics are dead. And that's not just your cell phones, your computers. All the power grid explodes, everything's fused shut. If you're in the wrong place, wrong time, your phone might literally explode and kill you. Like, they can do some really ridiculous stuff. And we'll get into like the absolute magnitude of what we're talking about here, but let's just say like we're pushing like 50,000 times stronger than like normal devices that you would expect, and not just where you are, everywhere at once. And that's where it kind of gets a little ridiculous. Yep. And also, just in case, it happens from both atomic and thermonuclear weapons. It's not necessarily tied to fission or fusion. It's actually tied to how radiation interacts with the atmosphere. So anything radioactive can theoretically generate EMPs if you have a high enough amount of radiation. So next slide, we have a couple of the circuits. I couldn't really fit them here. And we'll do a brief discussion of these various types of techniques. So a traditional nuclear EMP is a nuclear detonation. And what they do when they do that is they don't just generate like one electromagnetic pulse. They generate like millions and millions of them all at once across the entire frequency spectrum. A nuclear EMP, and most other types, solar flares, lightning strikes, are inherently wideband. That is, if you're listening on a radio station at 190 megahertz, you're not hearing anything, your radio explodes. And if you're on your 5 gigahertz Wi-Fi, that explodes at the same time. And those are literally 5 billion hertz apart from one another, and they still both are affected simultaneously. So it affects everything at once indiscriminately in all directions. But, and then this concept, if you ever hear this in industry, is called DC to daylight, as in 0 hertz all the way up to 300 billion hertz and beyond. 300 billion, 300 gigahertz, right? So, narrowband EMPs are what we're going to talk about later. This is the more useful version. Because realistically, unless you are looking for mass destruction in a strategic sense, a non-discriminate mass EMP hurts you just as much as it hurts your opponents. So in reality, from a tactical perspective, we look to build controlled systems. And that's where high-power microwave technology comes into play, and also broader electromagnetic weapons, but we're going to focus on high-power microwave for this talk. So, EMPs are electromagnetic waves. All it really is radio waves moving through the air who just happen to have ridiculously high power amplitudes. Far more than you would ever think. Like, you can receive radio stations 20, 30, 40 miles away. They could be coming off of a 1,000 watt or maybe even a 10,000 watt transmitter. And the volt per meter E field, which is how you measure the strength of an EMP, where you are, if you're 40, 50 miles away from that tower, is still probably going to be not even a single volt per meter, probably far lower. An EMP dwarfs that by a long shot. You're talking 10, 20, 30, 40,000 volts per meter everywhere at once. So it can be pretty ridiculous. But in terms of controlled EMPs, one of the main things you're going to focus on is antenna systems to focus it. Again, we want controllable. We don't just want it going everywhere at once. We kind of want to focus it like a laser. And that lets us aim it out. And then we'll discuss these circuits coming up. But a good method for generating EMPs, and if you go on YouTube and type EMP generator, this is what you're going to get, is switching high power inductive loads. Does anyone here know how a boost converter works? It's the common type of switching power supply that we use nowadays. Basically, it's doing the same thing. If I give you 12 volts, and I say, okay, here's 12 volts, give me 24 volts, but you have to stay in DC. You don't get to go AC, transform it, amp it up, bring it back down. You don't get to do that. In DC, we have methods where if you switch an inductive load on and off at a certain frequency, you can generate voltages that are above your supply voltage. And there's a lot of physics that goes into that. We won't touch on it today, but it's a well-documented phenomenon. And this is kind of a demonstration of that. We'll talk about some of these in a second. These are other methods. This is my personal favorite. But what I'm referring to here, if you have an inductor, which everyone here is familiar with what an inductor is. If not, I can explain it just briefly. Yeah?
Yeah, I would like an explanation.
Oh, perfect. This an inductor as the actual passive. So everyone knows capacitor is two conductive plates near touching, but not quite. And then they have their cables, right? That has capacitance, and it can store an amount of charge at a given time. Electrostatic discharge, it holds it. An inductor is the other reactive passive element. So there's resistors, capacitors, and inductors are the traditional four passives you get. The inductor is the opposite of the capacitor. It's legitimately just a coil of wire. That is it. Now you can add things that it coils around, whether it's a ferrite or some other material to enhance its performance. But broadly, all the inductor does is instead of a capacitor where it stores charge, the capacitor or the inductor resists changes to current. So basically a good way to think about it, a capacitor, as frequency increases, the capacitor goes from being an open circuit to a closed circuit. And for an inductor, as frequency increases, it goes from being a closed circuit to an open circuit. They're the opposites of one another. And that's a very useful piece of information to know from a circuit design perspective. That's how you build things like oscillators, which are, the basis of functionally all modern technologies. So it's good stuff. And inductors are awesome. They're cheap. They're one of the only components you can make well on your own. You just legitimately buy a wire and coil it. The formulas are very simple. They actually just ask how many times do you coil it, and that's it, which is nice. But what happens here, we talked about the inductor. When you have current flowing through the inductor here, you turn it on and your voltage goes up. And then you go steady state and it goes there. But when you switch it off really fast, which is shown, this was a steady climb, but this is a fast turn off, you have what's called back EMF. And what happens here, you notice that the magnitude of this back EMF is drastically higher. It says negative, but it's still drastically larger in magnitude than the actual DC voltage would have been if you were talking merely resistance. And the reason for that is, again, it resists a change. So while this reaches a very high peak voltage, it is not cheating thermodynamics. Energy is not coming out of nowhere. It has very little current behind it. So it's a very large static voltage, but it's not a high current, not a lot of energy there. There are tricks to make use of this stuff. This is how your computer power supply works. It's how it generates all the voltages with high efficiency. This, by the way, when you see inductors and EMF, does anyone know a very common type of inductor? The humble electric motor is just a big coil. As such, note for any of you who ever want to design a circuit with a motor, put a diode reverse biased across the terminals of the inductive load, aka the motor. Because guess what happens if you turn off the motor? You get a massive negative voltage spike that destroys your computer. This is good knowledge just for the future. But in most cases, you want to suppress this. But in our case, for EMPs, we want to use it. So any type of inductive load switching, you can generate these types of spikes. And these spikes can be used. But we're going to talk about another one real quick. This is known as a Marx generator. Again, if you've gone online and looked up like high power spark things, Electro Boom has built these before. What this is basically a breakdown generator. What you'll notice when we go through these designs here is the basis of generating an EMP is almost always find a way to trick the circuit into behaving high power for a split second. Because the point of an EMP is not to continuously radiate with massive amounts of power. It's to have an extremely narrow interruption that destroys everything in that exact moment and then disappears. So how the Marx generator works when it has a charge-discharge cycle is it's just a bunch of capacitors connected together with some resistors, and these are very high-value resistors. And then you have a spark gap switch, which is just a fancy switch that the second you reach a certain voltage, the air breaks down and it creates a conductor of plasma, being the spark. Once you've built up to a certain level, or you purposely cause a spark, you can also use a lighter. It counts as plasma. All of the spark gaps short all at once. And you can see the effective path here is highlighted with dark. So when the spark gaps are off, they're just open circuits. The second the spark gaps close, however, all the capacitors have just lined up and become one massive capacitor for a split second, and they can generate a massive voltage spike right there in that moment. So we're talking, you could take a 9-volt battery and generate 20,000 volts right there. And again, this is made of capacitors and resistors. That right there, that assembly, you could probably make it for 20 bucks. So that's the first step, is generating these high voltage signals. The next step we're going to talk about a little bit is how to actually make use of them, how to direct them, that kind of thing. But this right here is a very famous method. Yeah?
Are those capacitors in series? The diagram would have me believe that.
Here they're in parallel when the spark gaps are open, and then the moment the spark gaps close, they all go in series.
Wouldn't that be reducing capacitance though?
It reduces the capacitance, but the overall energy is amped. Because what is it? Capacitors in series. Capacitors in series work with resistors in parallel, so it's like, should be like 1 over C. It should be 1 over C equals 1 over C all over 1, I think. Yeah, something like that. But I think capacitors in series amp the voltage across them, and capacitors in parallel amp the capacitance across them. If I remember correctly. No one else had their hands up? Yeah.
So what if on your Marx generator circuit down there, instead of resistors, they were inductors? When you created that spark gap, would their resistance to the current change negate your sudden spike in voltage?
So if they were inductors in this stage, and they'd stay that way, they would act like a low value resistor, because it's just technically a DC steady state. After they've given time to settle, it's just going to be a wire, but it's a lot of wire, so it has a resistance, but it's not a high resistance. So it would behave like a resistor, but because of the impedance of the inductor, since the spark gap is a far lower resistance path in that moment, it would still dodge it. So if you did inductors here, it would charge faster because the resistance is lower, thereby the capacitor time constant is lower. But when the spark gaps close, it would not change its parameters too much. It would still get bypassed by the spark gap because it's far lower resistance of a channel than the inductor would be. And also, as you said, the inductor would resist a change. But I see what you're trying to get at with the fact that this would happen. And the answer is some wacky stuff would almost assuredly happen, because after it depends, because certain one of these would behave different ways because they're at different voltage potentials. So the answer is, if you have LT Spice, you can open up LT Spice and plug it in and check it out. That's free, by the way, that software. But it's an interesting question, but because of the nature of how this circuit topology is set up, it wouldn't behave exactly like this. It would have a different effect. I am leaning towards saying it would bypass it altogether, though. But this right here is a very old method, but also a very useful one. And this has been used to generate ridiculously high magnetic fields and EMPs. And of these techniques, taken on their own without any optimization, this is by far the most successful one. This is called an explosively pumped flux. It's a, what is it? It's an explosively, trying to remember the specific name.
Flux compression generator?
There we go. It's an FCG. It's a flux compression generator. Did I tell you about that, or you knew it?
I've done some research.
Okay, good. This is an FCG, and specifically, it's an explosively pumped FCG, flux compression generator. What this is merely an inductor, same deal, just a coil of wire. The coil of wire is wrapped around a copper cylinder with a little slit cut through it, so it's like that type of cross section. And then around it is a comical amount of explosives, like a lot. And these are high explosives. We're talking their velocity of detonation is way into the illegal territory. So doing this at home is not going to happen without a lot of licenses, which you can get. But basically, so you have this assembly. And as you can see, all it is closed wire. You have a switch here, and then somewhere you have this remote capacitor bank. Remote, because it's going to explode. So it's got to be kind of a distance away unless you want to lose your capacitors too. What happens here, this capacitor bank is massive. The bigger the bank here, the better you get here. Because, as we mentioned earlier, there's this concept of oscillators and how you build them using inductors and capacitors. The moment you close this switch, and this is a fully charged capacitor bank, it'll dump a massive amount of energy into this inductor. And you can do some math to time the exact moment that this curve peaks, and you have the maximum current in the inductor, and at that exact point, you explode it. And when you explode it, what's happening is the explosives are, as the name would suggest, compressing this whole assembly in. And when you do the math of an inductor, one of the things that's important is the loop area. What's the diameter of the loop? Well, what you're doing here, this is why it's important, it's high velocity explosives. You're compressing this system so quickly that the physics start to break down and behave a little weird, to where the inductor had this massive amount of energy, and then from its perspective, it's almost like you swapped it out for a smaller inductor, who under normal circumstances would have never reached those peak energies. And when you do that, compress it, out this axis, you can see this magnetic field, it sends a ridiculous magnetic pulse in that direction, normal to the loop area. So it just shoots it out that way. This was very popular. It was invented at Los Alamos, I believe. And then the Russians have a different version, of course. This one, of all of these, this is potentially one of the more useful ones to try and get it to be small if you want to make a tiny one, albeit you have to give up the fact that it's one-time use. The other ones, you can use them over and over again, and it's a lot better. But, any other questions on these? Otherwise, we'll move on and keep going. We'll hit some effects. So, the primary purpose of an offensive EMP is to destroy things. And pictured here are just a bunch of common catastrophic failures. If your objective was to completely disable something permanently, this is how you do it, right? You have various types of things. You've got capacitors, inductors, resistors, transistors, integrated circuits, and then integrated circuit kind of encompasses every other component you could really think of realistically. And then what happens here? Fundamentally, the EMP is producing unintended voltages all over a circuit. So for example, your computer has a power supply for a very specific reason. It's only assuming certain voltages, certain power levels on all these different buses and cables throughout the whole system. But the best part about the EMP is it's going to bypass any type of filtering, anything like that, and it's going to simultaneously get onto every single wire in your system. Some better than others, and we'll talk about how that happens in a second when we get to optimization. But broadly, you can just introduce random voltages at random magnitudes and at random frequencies all over the place where they're not meant to be. And just for example, has anyone ever put in a capacitor in a circuit backwards and just exploded on the spot? Yeah. EMPs just do that. They can just change polarities. Like if you had 5 volts DC on a line and the capacitor's like, oh, that's fine. And then you send an EMP, it could very well be negative 10 volts and it just explodes on the spot. That's the benefit. And you can optimize, and the more information you have about your target, you can make EMPs and microwave devices specifically to target like a certain phone, if you get really clever with it. And that's where you start getting into clandestine applications, when you start getting to like the super spy stuff where they're like, we need to fry this specific camera for this specific operation. You can do stuff like that. But that gets into like, we'll talk about optimization next slide. But basically, you'll pop caps, you'll burn out transistors, you'll burn out integrated circuits. But these are what's known as catastrophic failure modes. This is what people like to see, but it's not always the most important or necessary mode. The issue with a catastrophic failure mode is it requires a lot of power. And if you're over long distances or stuff like that, you might not have that benefit. At the end of the day, radio waves drop off in energy density as they propagate in space. So unless you're really close, it's unlikely a synthetic EMP will generate a full catastrophic failure mode and blow something up. But that's not always necessary. Catastrophic is one of the modes we discussed. And for nuclear EMPs, it's the dominant mode that kind of just destroys everything. But unless you're carrying a nuke around, you probably have to make better decisions. So, from a human-made EMP and HPM standpoint, these things aren't always capable of inducing catastrophic failure modes. And instead, you're looking to do something that isn't quite technically jamming. It is EMI, it's electromagnetic interference, where jamming seeks to interrupt like a radio. or other types of communication systems by just jamming what it's listening to without actually doing damage. When you're doing interference, you are physically coupling onto circuits that you're not meant to be and inducing failure modes, but those modes are rarely catastrophic failure. Instead, for example, if you had a signal that you're relying on, let's call that a data stream instead of a sine wave, so you're looking for bits, you're communicating latitude, longitude, let's say it's a drone, you're communicating rotor speed. My EMP sort of looks like this. It's a bunch of really weird noise, unexpected, hard to handle, but imagine it would be far larger magnitude to the point where you almost wouldn't even be able to discern that there's a sinusoid under here anymore. When you do that, the computer can't read it anymore. So EMPs and high power microwaves let you jam out at the hardware level instead of at the receiver or the software level. So you're not battling algorithms anymore, you're just battling physics. So in a lot of instances, this is easier to do and more useful to do than actually attempting to intelligently jam something like a radio. There's a lot of fancy ways for a radio to prevent itself from being jammed. The only way to stop yourself from being EMP'd or high power microwaved is to fully shield your system. That's heavy, that's expensive, and a lot of high power microwave applications are targeting drones. The point of a drone is to be cheap and expendable. Shielding them would drop their effectiveness, make them more visible to radar, and would, of course, increase their expense almost doubly so. So it's a good thing to force your enemies to try and shield things. Now, real quick, because this is actually some cool stuff just to know as good lore. We're going to talk the nuclear EMP event real quick. So this is a very specific thing. And they have this concept of the phases of the nuclear EMP event. There's E1, E2, E3. E1 is what everyone's familiar with. It's the flashy instant kill. It kills every electronic device in the vicinity, basically instantly, within a nanosecond, up to like a microsecond. It's the fastest pulse. And here's where we start getting to some numbers. These fields can easily exceed 50,000 volts per meter everywhere around you at once. You could be hundreds of miles from the EMP, and you're still seeing 50,000 volts per meter. A cell phone, 1 centimeter from your face, is 10 volts per meter. And if it was many hundreds of miles away, it would be nothing. So the magnitudes here at play are really ridiculous, and let's just be happy no one likes to drop nukes willy-nilly, because can't really do anything about that. This one is interesting, E2. It's the intermediate time pulse. This one is generated from the neutron effects. E1 is from gamma rays. And has anyone taken a physics class and heard about Compton effect, Compton scattering, anything like that? That's fine. There's a lot of really cool nuclear physics going on here to generate this kind of stuff, and we've made use of it in the past for various technical reasons. But if you ever have interest, you can hop on the Wikipedia. There's a bit more in-depth information as to how these various radioactive things are capable of generating radio waves out of nowhere. But E2 is neutron dominated, lasts for about 1 microsecond to 1 second, and it's basically lightning. It's very similar to lightning. This one's considered the easiest to defend against, except for the fact that E1 just happened and destroyed everything. So all your defenses are actually gone. So it's actually really bad. It's just more magnitude, more pulse, and it's going to really start breaking more stuff. Anything that survived the first one has now lost all of its filtering and shielding, and now it's going to get hit again. And then E3. In my opinion, E3 is the most interesting one, and from an infrastructure perspective, it is by far the most dangerous. This one can last for 10 up to hundreds of seconds. So we're talking minutes now, and this is still happening continuously. And it's because the nuke is so ridiculous that it distorts the Earth's entire magnetic field around it when it explodes. And then this type of pulse destroys power lines. Power lines are functionally just really long antennas, and when you're talking about signals that are lasting tens to hundreds of seconds in their oscillatory periods, you just made a really nice antenna for it to receive all that power. And it does. There was a Soviet test in the 60s that was trying to demonstrate this. They did this over a population center, by the way, their own people.
That's good.
Yeah, don't worry, we've done that too, but not as much. And basically, they demonstrated that these E3 pulses were capable of destroying 570 kilometers of fuses and voltage protectors all at once. They thought it was like this experiment was to see how much it would destroy. And they're like, yeah, it would never get this far, it just destroyed everything. They're like, should have done more wire, right? It happens. And also, to note, the nuclear magnitude of this explosion that did that damage was 300 kilotons. We have detonated devices in the 10 megaton range. Now, to be fair, modern nuclear warheads are in the range of 300 kilotons. We have dropped their size. As we've increased the precision of nuclear delivery techniques, we no longer need to vaporize continents to hit our target. But back in the day, they did. So that's why we ended up with 20 megaton nukes. So for optimization, we've got a couple slides on this. Actually, I think I'm actually just going to explain these out loud. But optimizing your electromagnetic weapon requires that you understand your target at a base level. If you're trying to be very sophisticated, the real answer here is the more sophisticated and deeper analysis, like reverse engineering, other stuff you have about your target, the lower power you can get away with. Because when you optimize really, really well, you can specifically lock in on one single component that's integral to the entire system functioning, and you can kill it. And that's expensive. Not to make it happen, but expensive to learn how to do it, because that requires a hilarious amount of testing. There are labs who do it, but that's 24/7 testing for months on end for a single device, just to figure out that one failure mode. But it's useful work. Yeah, unless you have a nuke sitting around, you will not be able to generate a wide enough bandwidth signal to hit everything at once. Because, yeah.
Is just targeting that one device, just the way you take it out, is targeting one specific frequency?
Depends on the part. But most of the time, you would like to narrow the frequency as little as possible so you can maximize the energy at that level. But picking your frequency or frequencies, you can also do multiple frequencies at the same time, and not even as a band chunk, you can do them discrete. But, and we'll talk about that in a second, but you would like to, and it depends on what you're trying to kill. For example, let's say you're trying to kill a capacitor. The capacitor, at the end of the day, by the way, what you want to do is model every single part that you want to kill as an antenna. Figure out how it best receives energy as an antenna, treat it as such, and then figure out frequencies based off wavelengths and some of the other stuff we'll talk about in a second. But functionally, yes. You want to narrow it down if you can. Sometimes you have no choice but to do multiple frequencies at once. In the case of complicated computing devices, like large integrated circuit CPUs, it might be best to focus on several hotspot frequencies. This kills the memory, this kills the CPU itself, this kills, that kind of thing. Yes. So, now we'll talk about these things to consider. So, this right here is everyone's probably familiar with the frequency spectrum. And when I say DC to daylight, that means all the way over here, where it's, 0 or 1, all the way up to basically infinity technically, but for our purposes, we're really stopping at around here, like 300 gigahertz. Now, the same principles that generate the radio waves are also going to end up generating all of this too, but it just so happens we only care about the electromagnetic portion of this. This is all technically electromagnetic, but in our case, we're talking about radio waves and specifically microwaves is what does the most damage.
So would nuclear weapons change anything about light when they go off?
They create light. Not as a joke, they physically make it. They do a lot of things. There's special types of radiation that generate special types of light. If you've ever seen a reactor turn on underwater, the blue glow, the Chekhov radiation or Cherenkov radiation, that's a specific type of radiation interaction that generates photons. So radiation can generate a lot of funny stuff.
So you said that some EMPs can be engineered to target certain components. Couldn't someone on the receiving end of that anticipate such a target and create their device with a variant? Like they could go to Intel and say, I want this type of CPU architecture, but make sure it's operating on this slightly different. I'm not an electrical engineer, so I don't know the terminology, but they would engineer a variant of it. And then whenever whoever is targeting them, launches their attack, the receiving device just gets passed up, like nothing happens. Is that a thing? Is that?
Yes. There are entire career fields. So everyone's familiar with, let's say, a CPU or a stick of RAM, that kind of thing. And you just buy a normal one. You know, maybe there's a bit of difference between the manufacturer, but you're gonna buy your bang for your buck, whatever you think is best. On our end, on the government, we don't do that. We have special fabs. We don't buy bulk from China or bulk from Taiwan. We have in-country fabs whose sole purpose is to design and fabricate what are called hardened components. Components that can handle gamma rays, X-rays, electromagnetic pulses, that kind of stuff. So we have special techniques, whether it be through shielding the component, whether it be through special fabrication processes that can drastically improve their survivability under adverse conditions. So the answer is yes, and there's quite a lot of money made in that field.
So I don't know how to phrase my questions like everyone else. I'm not an engineering major, period. Like if it just creates the light, that's just it, like it just stays?
I mean, the light will travel and eventually get absorbed by something.
So,
It creates the light in the instant of its explosion and then eventually stops once the radiation effects have gone down.
so it's just there until it's just not, basically.
Basically. There's a funny thing, the way that, there's a lot of ways to detect a nuclear weapon has gone off, but let's say someone's trying to sneakily test nuclear weapons or detonate them, which is something that has absolutely happened hundreds of times. The United States and the Soviet Union used to do this all the time. We're like, okay, let's stop doing that. But of course, neither of them trust each other. So they both sign a treaty and they say, we're both gonna put a bunch of sneaky sensors around the planet just to make sure the other guy's not cheating, right? And there's a famous one of these that the US developed called the Villa Hotel satellites. You can look them up on Wikipedia. They're unclassified now. There are images of them. They look really goofy. They kind of just look like two spherical solar panels. But the point of the Villa satellite was because we had done enough studies. The United States has done around 1,500 nuclear tests that are publicly disclosed. So we have a lot of information on these things. The Villa satellites were designed specifically to detect what's known as the double flash. The nuclear weapon goes off, there's an initial burst of radiation light, and then there's a drop, and then, because that light is very fast and instant, and then the actual thermonuclear heat generates a second flash of light that they can then be like, okay, let's see. Every other light source doesn't do this in nature, and they're like, but the nuke specifically looks like this. So they had a way to easily photograph these things or fingerprint them. Yeah, go look up the Villa incident and see what happened there. That was funny. But I digress. Things to consider with regards to optimizing. So we discussed a couple things here, but we'll talk a bit about in depth what's going on. The physical size of your target and specifically your target's components. Often you're not hitting the target broadly unless you don't know a lot about it and you're just shooting to shoot. Normally you're aiming to target components, although you can often assume most things use common components that are available. There are instances where you have critical hardware, like he mentioned, that is protected. But in the case of a protected critical component, then you go down the tier list and start attacking less critical components in hoping to induce a chain failure or something like that. So information on the target component, physical dimensions, we're talking centimeters, millimeters, inches, whatever, because that will inform the selection of your wavelengths, which informs the selection of your frequencies. Polarization effects. Is everyone here familiar with what electromagnetic polarization is? I have a slide in I have the next slide that I'll actually show you this, and I'll explain it a bit if you're not, but that's fine. Actually, real quick, we'll hop over to it just in case. Yeah, we'll just quickly hit the rest of these real quick. Antenna effects. As mentioned, for our purposes, you don't just want to blast it in all directions because you hit yourself. So you need to actually focus it. Antenna theory is complicated. We're not going to touch on that in too much depth here, but the answer is use a fancy parabolic dish, use a fancy phased array, and you can probably get a nice laser-like beam that you can aim this radiation in a specific direction. Hardness of target, which is what we discussed there. Certain components require higher peak powers because they've been protected. There's a way to bypass. There's no such thing as an invulnerable part. Enough power, you will kill it. The answer is, can you afford that power budget? Right? And then the last thing is range. This radiation drops off with effectiveness over time. So if you need to consider for your strategy, how far is this thing going to be on average from me, that also informs your antenna design and that informs your power requirements. And now we'll talk the polarization stuff. So this is a slightly confusing but not crazy confusing picture about polarization. Electromagnetic waves, we can visualize them as oscillating electric fields, and then 90 degrees from that, you have an oscillating magnetic field. They're always together. So they're both going, side, side, up, down at the same time as they travel. There's the concept of polarization, which is the whole wavefront has a preferential position as it's oscillating through space. So let's say, for example, and then polarization is defined by the E field. We ignore the magnetic field. So wherever the E field is oscillating, that's our plane of polarization. So if my E field is going up and down, can anyone guess what polarization that is? Vertical. Yeah. It's actually fairly intuitive. It gets a little weird with circular, but it's not that crazy. So when you're thinking about it, to conceive of what polarization you're looking at, if the wave's traveling at you and it's oscillating or moving or 90 degrees from your point of view, and you were to trace its oscillations on a piece of paper, what does it look like? So if you're looking at it and it's oscillating up and down, that's vertical. If you're looking at it and it's going side to side, that's horizontal. Those aren't the only rules. You could have a 45-degree linear polarization. It would just be half vertical and half horizontal, and it would end up like this. And this is how you have things like dual polarized, cross polarized. These are just superpositions of these two. Legit, like they just added them together. It's not super complicated. You can kind of ignore those. These are a little weird. Circular polarization. And unfortunately, this is what you have to do. So what this means is instead of the wave going up and down or side to side, the wave is rotating about its axis towards you, kind of like a corkscrew in your direction at all times. A little hard to conceive of, but the reason this is important is because of how polarization works. If I'm holding my antenna, let's say it's a rod, vertical, and a vertical wave hits it, I receive it perfectly, 100%. If a horizontal wave hits it, I get none of it. Polarization has a massive effect on how energy couples. And it's actually very useful for communication. It means you can use the exact same frequency, and as long as your polarizations are sufficiently different, you can talk and receive at the same time. That's how mobile technology works, among other things. But because, as we said, orientation now matters. Let's say you're looking at a drone who could be flying in a bunch of different directions relative to you. Well, if you just aim, linear polarization of vertical, horizontal, whatever at it, maybe half the time, maybe 7% of the time, maybe 10% of the time, your energy's doing nothing. It's just not even interacting with it. The way to optimize for geometry or orientation that you have no control over, you won't know ahead of time, is circular. Because it's always changing, so you'll maximize the likelihood that your energy does what you want it to do. Yeah.
Do we have to sacrifice some of the energy to make it be spread around like that instead of staying in one single polarization?
So luckily for polarization, you don't have to sacrifice energy. It's not like frequency where you do have to spread it, because each frequency is a separate signal. Polarization is inherent to a signal, but it is expensive. Polarization is imparted by the antenna. So you design your antenna to have a specific type of polarization. So when you're talking circular polarization, it's a more complicated antenna geometry, so it's generally pricier. To get a really nice beam, a circular antenna is going to be a lot trickier than, let's say, a linear one. Because a linear, it's simple, it's easy, it's like, oh, it's just straight. But the geometries of circularly polarized antennas, let me see if I can find one really quick. A common style is a spiral antenna. What on earth is this? There we go. Oh, it keeps trying to make me do this. Chrome is being rude. They're being real, okay. here's a fancy one. You guys actually may have seen these in public. These do exist, but this one would be terrible for our application because it's not a laser by any means. It's in all directions. But circularly polarized antennas are more complicated. Here's a more fancy one. This is a type of spiral antenna. So it's this really weird shaping. This is a little better, but still not great. So it increases complexity, but luckily you don't have to sacrifice power to make this happen, which is optimal for our purposes. But yes, polarization matters. And just for the future, just so everyone knows, like polarization is extremely important for electromagnetics and also just light in general. I'm sure everyone's used like a polarizer lens on their glasses or something so they can, see in the sun. And the reason for that is the sun is a bunch of unpolarized, randomly scattered light. But if you focus really close in on random sunlight, what it actually means is you just have a bunch of light that is polarized in a bunch of different ways. So the reason you can see better is because you're just blocking a certain percentage of the light coming into your eyes when you have a polarizer lens. So there's a lot of tricks you can do in light and electromagnetics, and luckily the physics is identical. They are both technically the same thing. And then with regards to that, so you have polarization optimization, but then there's that thing I keep saying wavelength informs your frequency. Wavelength, which is given by lambda, which is just in meters. The wavelength, I actually probably should have done this. Like if we just have a sine wave, this is the wavelength. One cycle, length of one cycle. That's all it is. So how physically long is that one cycle? So for example, if you have an antenna and it's 1 meter long, that wavelength happens to very nicely correspond to 300 megahertz on the dot. So if your antenna is 1 meter long, it means it'll be really, really good at receiving 300 megahertz. And anything higher frequency, wavelength goes down. And the reason for that, this by the way, that's the speed of light, so 300 or 3 times 10 to the 8th meters per second, whatever you like. Speed of light divided by frequency equals wavelength, which basically means as frequency goes up, wavelength goes down. So when we start talking things like cell phones, or let's say you're 5G, you're operating in like the 3 to 4 gigahertz band, you're starting to talk like your wavelength's like 6 centimeters, 10 centimeters, starting to get shorter. Now, of course, these have antennas in them. So the question is, how on earth does anything happen? Because we know that, 6 centimeters is bigger than the phone, or at least bigger than large sections of it. So where are they hiding the antenna? And the answer is they paid some people a lot of money to invent antenna miniaturization. Yeah, it's a whole thing. That's where you start getting into metamaterials, which is really fancy. So we won't talk about that here, maybe a different talk. But the point is, and I think I mentioned it, no, not quite, I mentioned it here. Technically, the best thing you want to do is, let's say your part that you're attacking, for whatever reason, is a centimeter long. It has a conductor in it that can be modeled as a centimeter long. In that scenario, if you do this math, that equals 300 gigahertz as your frequency. So you should, technically, dump all your energy into 300 gigahertz and aim it at that device, and it should have a maximal receipt of energy, assuming your polarizations and stuff worked out. Well, I didn't put the picture in. Radio waves don't all go through the air. Most of them are blocked, actually. Once you hit like 2 gigahertz, you just can't go through the air very far. So then you have to start thinking, all right, can we get away with half a wavelength, a quarter wavelength, an eighth of a wavelength? So these are resonant modes. Your objective is to find a resonant mode that you can get a frequency of sufficient power to, whether that dimension is a wavelength, half a wavelength, a quarter wavelength. It can also be 2 wavelengths, 4 wavelengths, whatever it needs to be. That's an optimization problem. That's a little far for this one. But just keep it in mind, you can't always do what you want to, and you have to make do with what you can. Actually, I think I can pull that up real quick. See if we can find the famous chart. This is for light. That's not what we want. Here we go. What on earth? There we go. So this, starting at around 10 gigahertz, And this is attenuation, so this is energy lost over time, bigger number equal bad. And of course, it's in decibels per kilometer. A loss of just 3 decibels is half your power gone, like that. So keep that in mind. You can start seeing it gets a little ridiculous per kilometer at certain points. But like in that example I just said, let's say you had a centimeter, and we're all familiar most electronic devices are rather small. So that's fair to say. Yeah, 300 gigahertz, yeah, we're going nowhere, basically. 40 decibels per kilometer means 300 gigahertz reasonably goes no more than like 5 feet before your energy's gone completely. So you have to optimize for things. Keep in mind, not all warfare happens on Earth. Once you're in space, this isn't a problem anymore, and you can just do whatever you want, which is fun. We have satellites in space operating at 300 gigahertz without a problem. But yeah, so this is an issue, so it's something to consider with your design. This is why engineers get paid big money, because we basically get asked to just make things up as we go. Make the impossible possible. So now we'll just real quick hit up and talk about the subset. So high power microwave technology. This is the new golden goose. We can't very well drop nukes on everyone because that affects us and them and isn't great for diplomacy. So we have to be a bit more conservative in how we use this technology. So does anyone know what this is? You do. That's scary. So this device, this is a newcomer to the game. This is Apirius Technologies. Basically, they've devised this system, which is called Leonidas. Apirius, or Epirus, is where Leonidas was born in Greece. So they really nailed that one down. But this is their Leonidas HPM system. There are videos online now of this system taking down 50 drones in a single sweep, right out of the air. Just pops them all. And what this is, underneath this very fancy tan covering, is a very large and fancy antenna array that allows them to do that focusing. And that's what's necessary, because this thing is rather large, but not that big. And it's mobile, so it has power limitations. You can't just plug into the grid and do whatever you want, which means you gotta get really focused with your energy, otherwise you're not gonna have enough magnitude to do the damage you want.
Does it do that in a similar way to like a phased array radar?
Yes. I will say though, it does do things similar to phased arrays, but it behaves the same way, but it's not exactly an active electronically scanned array. There's a couple differences there. There are reasons, and there are things about active electronically scanned radars that fail when you start amping the power really high. Certain components just can't handle it. Their technique, and I think I mentioned it a little later on, but the new method is to use what's called a software-defined radio. And it allows you to do some fancy stuff. I talked about it a bit later on. This one is old. You can sell. It's not a phased array. It's a dish reflector. Same type of thing you'd see off the side of a house getting television. Just very big. This device is known as the Active Denial System. It's developed by the United States government. We've fielded it to a couple places, and a couple countries have copied us. This system is not meant to affect electronics, although it could. Not well. It's meant to affect people. This device is optimized with 96 gigahertz. So it doesn't go very far, as we saw with that propagation chart, but it goes far enough. This device is designed to penetrate exactly 1/64th of an inch into your skin and make you feel like you're on fire, so you leave the area. And it does no permanent damage. But it sure feels like it does. And that is the point.
What was that frequency again?
96 gigahertz. If you can generate 96 gigahertz, I mean, yeah.
Could you do permanent damage to a human that way?
Yes. We'll discuss that shortly. But, absolutely. Go home, put an egg in a microwave. See what happens. Now, microwaves, let me specify that terminology just so you guys know. The microwave, the device you're all familiar with for the Hot Pockets, that is a device called a microwave that does operate within the microwave frequency spectrum, but it's like 1 to 2 spectrum. It's like 2.4-ish, 2.3-ish gigahertz. And it's just right there. That was selected, optimized for heating water molecules. So it absorbs really well into water, turns to heat. The microwave band is 300 megahertz to 300 gigahertz. When you say microwave frequency, you're almost always referring to functionally all radio waves that we care about. Past 300 gigahertz, you're basically starting to hit like infrared light. And then below 300 megahertz, you're just starting to be like, all right, we're starting to be like, this is basically a DC signal, so we don't really care as much. Once you hit 500 megahertz, like on a PCB design, you have to start considering radio frequency effects. So that's where that kind of band comes from. But they do a bunch of fancy stuff with phased arrays, focus it up. In that case, it's a parabolic dish. So HPMs are different. They're not these big wideband systems from a natural perspective. They are specifically designed to be rather narrow. And how they do this is it's basically just a radio, and then the innovation is how well you can amplify it and how well you can amplify it with access to limited power. So, funny enough, if you guys thought vacuum tubes were dead, you're wrong. We're still using them. Absolutely. So, there are advances in silicon carbide technologies in the form of semiconductors, high temperature, high power handling semiconductors. They still aren't there yet for certain applications, particularly at high frequencies. When you oscillate as an RF wave, you're basically switching on and off really fast. Transistors are great when they're either on or off. But in the moment when they're swapping between on and off, they become a really shitty resistor. And in that moment, they love to explode. So they're not quite there yet. The vacuum tube does not quite have that issue, so they still are vastly preferred for extremely high power applications. Still very rare. You'll see a vacuum tube. Most people are only familiar with them because they either knew about them in the past or they happen to be a music nerd and insist that the tube has better sound quality, even though they're wrong. I assure you of that. But the main focus is on that energy amplification and, of course, supplying power. Advanced power supplies, advanced batteries, that's important, and then advanced power generation. Obviously, certain systems do make use of the tubes. High-end systems like Aperius and some of the newer stuff coming out of Raytheon, they have cracked the semiconductor problem and have their own fancy transistors that can handle the power. Or they have comically advanced active cooling systems to keep things under wraps. This is the aforementioned software-defined radio. Nowadays, as opposed to just having an analog circuit bank that you're swapping between, it's a hack RF.
No, we do radio astronomy on the project that I work in. We use AirSpies.
Okay. What frequencies?
1.42 gigahertz.
Okay.
You're on Terminus?
Yes.
I am too. Wait, oh you? I see you around.
But yeah. So software-defined radios, what they do is they basically digitize most of what a traditional radio's components are. So a normal radio, everything's handled entirely analog. It's all being processed, modulated, demodulated, mixed, down-converted, up-converted, whatever, all in analog circuits. That has a lot of inherent limitations. The primary one is any type of fancy signal processing is very expensive and very inefficient. And your bandwidths are limited badly. Your bandwidths get limited because passive components have bandwidth limitations inherently. So if you stay passive all the way through the system, you just introduce a bunch of issues. It can be done, but again, very expensive, very heavy. Software-defined radios, the signal comes in, received by the antenna, and is almost immediately sampled with a digital analog converter and turned to bits and sent to a computer instantly. And then when we want to send something out, bring bits out of the computer, put it to an analog to digital converter, send it out to the amplifier, boom. It's very flexible. They're cheap. This device is a commercial one. It's very strong. It has a crazy wide band, well, not really, has a crazy wide band of, it's like 1 megahertz to 6 gigahertz, pretty good. And it's about $300 on Amazon. It's a pretty solid price. Keep in mind, just because the device can do something doesn't mean you're legally allowed to. So if you do happen to mess with radios ever, just know it's very easy to press a button and be a felon. So don't do that. Try not to, at least. And particularly not in Huntsville, because the arsenal is listening at all times, and they get really mad if you go on S-band and X-band. But the effects A lot of the effects we've already discussed, it's not really worth rehashing it. They behave very similarly. This stuff does the exact same thing, except it is lower power, more direct, narrow band, and it's kind of more digital. It's a lot more fancy in how it behaves. So, real quick with these advances, the industry leaders are, Raytheon is the big one. They invented the Thor system, a lot of the other legacy HPM systems, and Aperius is a newcomer. A lot of the modern advances are related to better antennas. The better you can focus it, the less energy is needed at distance. And that's a really big area of improvement. And then the biggest thing, however, is the software-defined radio aspect. Aperius is the first one to really implement high-end software-defined radio behavior. So let's say this. Let's say your target needs you to jam or blast energy from 300 megahertz to 600 megahertz, that whole area. And you're standing right there, you're the operator. But your field radios operate at 400 megahertz, and you need to communicate with your guy. You're like, something's wrong, what's going on? Your system, the Aperius system, is capable dynamically of saying, oh, you need what band? And immediately cut out a safe zone for you to talk and then block it off again instantly. On the fly, fully dynamic. And when you integrate AI and other active sensing and control systems, you can do some fancy stuff where it's able to basically respond to your needs instantly. So it's very fancy. And it also helps with if you have to switch between multiple targets of different styles, all you need is a bank of each target's vulnerabilities and then completely change its properties for each target as it goes. Super quick. So this is the type of advanced stuff we're getting into. So real quick, we can do a Q&A. And then once the Q&A is done, I'll cut the recording. Did I say that over here?
Yep.
Yeah. So we'll do the Q&A real quick. And then we'll do this up so everyone can do a little quick sign-up thing when we do the Q&A. And then once Q&A is done, we'll talk about the last thing. Yeah.
What do you think is the coolest part about all of this?
The thing I'm about to say once we cut off the camera. But realistically, though, the coolest thing about what's coming up is that fundamentally, radio waves move at the speed of light. Most military technology, particularly in the last 100 years or so, has been focused on how do we use a bunch of sensors to cue a bunch of shooters, to cue a bunch of missiles, to guide them to a target, and then hopefully get in there in time and hit it, if not dodge it, whatever, and then destroy it to protect yourself if something's coming, destroy something on the way, whatever. Very expensive, slow, complicated, and there's a lot of areas for failure. Nowadays, we're starting to push towards the point where all it is, oh, we see something, bzz, because you can't dodge light. I don't need to account for where you're going to be, I just aim at you. It's a lot easier. A human could legitimately do this. Who needs an automated turret, right? That you just sit a dude on there with a joystick and just play like Space Invaders, and it could happen. We wouldn't do that because automated systems are better. But yeah, we're getting to the point where eventually, this technically counts as directed energy. Is a type of directed energy. You also have lasers and other stuff like that. Funny enough, there's a type of directed energy where they just blast neutrons. That one's fun. But yeah, there's a lot of interesting stuff coming on, but I do think it's kind of getting to the Star Wars territory, which is cool. Yeah.
I know we have treaties in place regarding weapons in space. Would something like an HPM weapon in place in orbit, would that be covered under that? Is that new?
I'd have to check the treaties, but most weapons in space treaties are specifically WMDs. You're not supposed to put chemical, biological, nuclear style weapons in space. What I'll tell you though is no one listens to treaties, so it doesn't really matter. The whole reason we had to put a bunch of satellites in space is because everyone knows. They're not going to violate it blatantly, but we're going to do a little bit. That's how it goes.
So in the early 60s, the Soviet Union and the US agreed to the nuclear test ban treaty, but it makes it so that anytime a country tests a nuclear weapon, well, anyone who's signed to the treaty, they have to test it underground.
Yes.
So does the Earth does it absorb most of the radiation so that?
Yeah, when it's underground, you don't have a lot of the EMP effects. They still exist, but it's not as bad. A lot of the EMP effects from a nuclear weapon occur because you airburst it at altitude, and it gets to affect the atmosphere, the magnetosphere, the ionosphere, all that kind of stuff.
So the Earth inhibits most of the
Yeah, if it's an at level, like on the ground or subground, there'll still be effects, for sure, but they will be subdued. It won't be nearly as bad. And I didn't make a specific note out to it, but I said there's like the 50,000 volts per meter thing. That's like the current known max that's expected from a high power explosion. There are reports of so-called super EMP nukes that are optimized for the EMP, although no one really knows publicly how much they could do. But there are ways. You can optimize your nuclear weapon for radiation. We have neutron bombs. So if you want to optimize for an E2 EMP, use a neutron bomb.
I hate to interject on that, but the reason why they didn't ban underground was because they didn't have any way of measuring it back in the 60s.
have any way of what?
They didn't have a way of measuring if Russia was nuking underground or not
Well, but
with the test
that
ban.
you're saying that they did.
They did not.
They couldn't verify it, so they
Don't
don't.
make a rule you can't enforce.
But
Yeah, don't make a rule you can't
has there
enforce.
been surface testing since then? I don't know. I just
I guess
remember
they
that.
just haven't been to the table since then, but I could be perpetuating bad information, I'm not certain.
I'm not entirely sure on that, but I do know we eventually do have ways to detect any nuclear explosion. So we have space detectors, of course, to this day. All GPS satellites are fitted with so-called bangometers, which is the official name of a nuclear detection device. Yeah, it's legit, not even trolling. But yeah, all our civilian GPS and military GPS satellites are outfitted. So at all times, we will know if there's an explosion in the atmosphere. Then we have devices at the Arctic poles and in some other locations that can measure, nukes are large enough that the whole Earth will vibrate enough to be detected. So we have arrays of basically earthquake detectors that can tell you, one, that a nuclear explosion has happened, and approximately where on Earth it has happened. And also, if the Earth vibrates, you'd expect that it would also send signals into the ocean. The ocean would vibrate a bit. So we have hydrophones as well in the ocean that can detect that noise. So there's a couple ways. Yeah.
So I know that drone warfare has been, especially in the public's eye since like Ukraine, has these like jamming, or not jamming, but these like high powered technologies, how long have they been in development?
They've been around for a while. The technology requisite to generate the powers in a mobile sense haven't been around for super, super long, at least from an efficiency standpoint. But Apirius has been in development and has been fielded and tested for roughly 5-10 years. Raytheon has had systems in play for the last 20-ish years. So I'd say the last 3 decades it's really been serious, but they've been investigating this for quite some time. But it's only been feasible and useful in the last 10, 20, 30 years-ish. We'll do him and then you.
Oh, me?
Yeah.
Okay. How does a nuclear, I don't remember if you said this, how does a nuclear EMP compare to like a solar flare? Well, on like damage.
Depends on the magnitude of the solar flare. The solar flare predominantly generates E3 effects. It doesn't have the speed necessary to generate E1 and E2. So it mostly just cripples your power infrastructure. So all of your, civilian infrastructure, of course, all electronics rely on it though. So you're kind of screwed either way. But a solar flare is worse in terms of absolute area affected. But your phone would still function, technically. Your computer is probably still okay, but not for long. Your battery will run out eventually, so that's the limit there.
Do you know if like the fly-by-wire drones rather than like traditional wireless drones?
You're talking about the fiber ones?
Yeah.
Yeah.
How they respond to a system like Everest differently than?
No, same effect. Because those drones are to prevent jamming, which is fundamentally different from here. Because jamming is a low power technique comparatively, because radio receivers are sensitive, and radio energy is generally low. So you don't need to send out a crazy amount of power to prevent a drone from seeing its controller signal. So they use fiber, so they can now fly freely, but that doesn't prevent them from getting fried. So this is a countermeasure to fiber line drones. And in 2 weeks, the next talk is on counter UAS techniques from Cummings Aerospace engineer Sean Mitchell, if interested. Any other questions before we cut the feed? Okay. You can ask questions after the feed too. I'm sure you're about to have some.